Dear student, now I explain the introductions to state estimation of power system. First, introduction. The monitoring of generation and the transmission system is useful in economic dispatch and load frequency control. And then, secure operation plays an important role in complex interconnected power system. Before we make any security assessment, a reliable estimate of the existing or current state of the system has to be made. The problem of state estimation deals with this and is addressed in this topic. The input to a conventional load flow program is the P, that is real power, and then Q, reactive power injection at the power P, and then modulus of V, that is the magnitude of V, values at the voltage controlled buses. Even if the problem is one of these values is unavailable, the power flow cannot to be run. Further, erroneous measurements can render to the power flow solution useless. Measurement of other quantity may be available, such as real power P and reactive power Q, line flows, bus angles, etc., which cannot be used in conventional power flow calculations. Then, in power flow calculations, we use a bus model or branch model of the network, which is used in the conventional state estimation. However, the network connectivity is normally described in terms of bus section switching devices. The network topology process is used to transform the bus section switching device model to bus branch model. The determination of real-time model from the available data is decomposed into two sub-problems: the processing of logical data or the topology processing, and the processing of analog measurements, that is observability analysis and state estimation. A conventional state estimation normally has the following set of variables and measurements. State variables, first one is node voltage magnitude and angle. Second one is transformer complex turns ratio. And then second one is measurements, node voltage magnitude and angle. Second one is active power flow in branches. The third one is the bus power injection, that is the measurements, bus power injection. Fourth one, reactive power flow in branches, bus reactive power injection, current magnitude in branches, current injection in buses, magnitude and angle of transformer ratio, turns ratio. When the set of available real-time measurements is sufficient to calculate the state vector, the system should be observable. When the system is unobservable, we have observable islands as well as unobservable regions within the network. So, the pseudo measurements include specified or target bus voltage magnitude and angles, target active power flow in branch, reactive power limits at buses, target current magnitudes, limits on transformer taps and phase shift. The first one is mathematical formulation of the problem of state estimation. So first, what is the state estimation problem can be formulated as a constrained optimization problem, that is minimize function z, z minus h of x. Then in this case g of x equal to 0, c of x less than or equal to 0, where z is the vector of measurements and then The h of dat is a vector function relating measurements to state variables. F of dot is an objective function. G of dot and C of dot are the vector functions representing power flow quantities. The most popular method is the weighted least squares method, where the quadratic objective function is used is given by f of z comma h of s equal to z comma z minus h of x the transpose t and then w into z minus h of s, where w is the diagonal matrix of the weights. For telemetered measurements, the inverses of measurement variations are normally used as weights. Equality and inequality constraints are used to represent target values and limits in the unobservable parts of the network. Now you see the network diagram. Then the left hand side, that means a Vk e power delta k, that is Pkm plus jqkm, that is closed switch. In the right hand side, Vm e delta m, that is the Pmk plus jqmk. So this diagram represents the branch with zero impedance. Then what is the zero impedance branches? Generalized state estimation is performed on a model in which parts of the system can be represented at a physical level in terms of bus sections and switching devices only. So in this model, that means include measurements made on zero impedance branches and switching devices. Now we consider the zero impedance branches, which is actually a closed switch or circuit breaker. Already we see now that is the figure and all. So therefore Vk minus Vm is equal to 0 and del k minus del m equal to 0. So therefore the sort of measurements are reduced to Pkm plus Pmk equal to 0 and Qkm plus Qmk equal to 0. Now we can use the Pkm and Qkm as a additional states only. Now linear least square estimation. The least square solution is used for estimating over-determined systems of linear equation. The equation is Ax equal to b. And then x is nothing but the vector of size n and b is the vector of size m only. In an over-determined state n, the number of unknowns, that means less than m, number of equation. M denoted for number of equation, n denoted for number of unknowns. First one is a formulation. The least square problem is to solve the n vector x for which the index j of x is defined as j of x equal to 1 by 2 into b minus ax transpose t and then b minus ax is minimized. The residual vector is defined by r equal to b minus ax. Therefore, the least square solution x vector is such that j of x vector is equal to minimum r transpose t and then r only. So, the determination of state estimate, second one is the performance inductance j of x vector is differentiated to get the optimal condition, that is dou j of x divided by dou x, and then the condition is x equal to x vector, that is equal to a transpose, that is the a transpose, that is t, a x vector minus a transpose t and then b equal to 0. So the a transpose, that is a t, a x vector equal to a transpose t into b, and then solving by x vector we are getting finally x vector equal to a, the power, that is the t means transpose matrix, a transpose t into a, the power is inverse, that is the inverse matrix, and then a transverse matrix t and then b only, where x vector is the state estimate. The gain matrix G is defined as G equal to a, the transpose t and then a only. So the pseudo inverse of a is defined as then a dash equal to A transpose T, A that is the inverse, and then A transpose, show that the x vector equal to A that is the inverse matrix, that is the dash into B only. So if that means if m equal to n, that is the number of equation equal to number of unknowns, m equal to n, that is equal to rank of A matrix only, then A inverse equal, that means A dash equal to A inverse only. Then observability, third one is the observability in least square estimation. The coefficient matrix A of size m into n is non-singular if it is has a full rank equal to n. In such case, the state estimate can be obtained from equation 6 and the system is said to be observable, which means we can estimate the circuit state from the available measurements only. Even if 1 meter is removed, that is m equal to n, number of equation equal to number of unknowns, the system is still observable. So removing 2 or more meters make the system partially observable or unobservable. Thank you student for watching this video.